Okay, everyone. One last topic that I want to discuss in the context of phase diagrams of mixtures, and those are temperature composition diagrams. Previously, we talked about pressure composition diagrams. Today, we'll talk about temperature composition diagrams. And I'm not going to go through a long derivation about these types of things. You can read about some of it in Atkins. Let me just point out to you that this is what the temperature composition diagrams look like. Right? Previously, I had one straight line and one curvy line. Now we have two curvy lines that sort of form an I shape. And so let me go through and just ask some questions, which I think will help calibrate you about what's going on with these. So first, let's label the phases. And if you think about it, right, at low temperatures, liquids present. At high temperatures, we have gases present. And in between, we have liquids and gases. It's two-phase regions. Which component, A or B, is more volatile? Well, we're not looking here at vapor pressures. We're looking at temperatures. And specifically, what these points on the end correspond to are the boiling points of pure, this would be A, and this would be B. Right? So those are the boiling points. Which ones are more volatile? And the answer is this one. Right? The reason it's more volatile is because it has a lower boiling point. Right? The interactions are more unstable. Last but not least, if I start at point X, identify interesting points that may exist as you start to heat the mixture. And so if I start here and start heating this, I have pure liquid, liquid, until I hit this one. Right? Then gases start to form. Right? So this would be what we call the bubble line. So here it begins to boil. It will continue boiling, boil, 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 boil. You're going to have less liquid, more gas. Right? It's going to boil, boil, boil until you hit this point, at which point it's totally vaporized. Oops. And as I keep going, you get the pure vapor. Right? The qualitative ideas are the same as the pressure composition diagrams. So hopefully that's useful. One important use of these types of diagrams are for distillations. And so I want to walk through this. This will tie in with something that you have seen in organic chemistry. So if we start at point A1, let's walk through a distillation process. And this will look very, very similar to what we just did. Right? So as we start to heat this mixture, we will heat it until we hit this point T2, at which point the system will begin to boil. So the vapor that first comes off is enriched in the more volatile component. That's the one at the lower boiling point, this one. And the gas, the vapor, right, that first comes out of the liquid mixture has this composition here, defined by A2 prime. You then imagine taking this liquid and condensing it. I said liquid, but I meant vapor. You take the vapor at A2 and then you condense it to a liquid. That will happen if you can cool it to temperature T3. Composition of this liquid is the same as it was here. We haven't changed anything. And then you boil it again. Okay. So if I boil that liquid to a gas, it now becomes enriched in A, whatever this thing is. And then you just repeat this cycle. And at the end of the day, what you can do by doing this is purify your liquids. My son's out mowing the lawn. I don't know if you can hear him. So this idea here, these number of cycles that you would have to go through. Oh, my pen died. So I can get it to come back on. This, and this are called the theoretical plates. The number of condensation and vaporization cycles that you'd have to go through in order to purify your liquid. All right. This leads to one less interesting topic then, which are non-ideal mixtures. Everything we've been talking about up to this point has been an ideal mixture. And so the question is, can you separate all liquid mixtures by a simple distillation? And as you may remember from organic chemistry, the answer is a resounding no. You cannot. Mixtures that can't be separated by a distillation are called azeotropes. And in short, what they are liquid mixtures in which the liquid and vapor have identical compositions. So this is what the phase diagram of a non-ideal system looks like. Rather than that I-shaped, you get this dip where both the vapor and the liquid have an identical composition. And this is called a low boiling azeotrope, right? Because the boiling point of the mixture is less than that of either of the pure liquids. An example is ethanol water, which boils at 78 degrees. One question we commonly ask is, what are the nature of the interactions in this azeotrope? Are they stabilizing, destabilizing, or ideal? And if this is boiling at a lower temperature than either of the pure liquids, what you might guess here is that there are destabilizing interactions, lowering the boiling point of the system. Oh my word, I just wrote it over myself. I'll read it to you. Results from unfavorable AAB. It takes less energy to overcome those interactions. If there's a low boiling azeotrope, there is also a high boiling azeotrope. This is one in which the mixture has a higher boiling point than either of the pure liquids. An example is nitric acid water. And this results from favorable AB interactions, right? Stabilizing interactions, where more energy is required to overcome those interactions. And I think I'm going to stop here. This is sort of all I have. Hopefully this will allow us to answer those, not those, there's only one primary question that we wanted to ask, which was, how do we interpret phase diagrams of liquid-liquid mixtures? All right, stop here, and we'll see you next time.